Thank you very much. I'm going to stand over here so I can cheat and see my screen while I go. So I'm very excited to be here. I hope we can have a fun discussion. So don't hesitate to stop and ask me questions and things as I go. I should admit a little bit of overselling in the advertising here. So in the title I say, learning semantic parsers for more languages with less supervision. And you should actually change that and to an or. So we're not doing both of these things at the same time. One half of the talk I'll talk about more languages. One half of the talk I'll talk about less supervision. But you see it all sort of fits in the same framework. And we'll talk about what we need to learn in the different settings. Okay? So where are we? So what is this notion of semantics and meaning? And I would argue that there's a whole spectrum of different types of problems where you take text and try to recover the meaning of it, right? So you could think of information extraction as one of these tasks where you've got some text and you're trying to pull out facts, like the fact that Obama is president or maybe is president of the United States. And the goal here is to go really big. So we're going to try to do all the text. We're going to look at everything. But the amount of semantics that we're pulling out is maybe relatively shallow. It's a bunch of facts. Right? And then maybe somewhere in the middle we have something like broad coverage semantics where maybe you're doing some role labeling or looking at different aspects of verbs and you're going a little bit deeper with the semantics, but you're still trying to do lots and lots of broad coverage text, and so you're somewhere sort of in the middle. And actually, I'm solidly way over on the other end of this axis, right? So what I'm going to talk to you about today is a relatively limited domain text, but a relatively complete representation of meaning and semantics, right? And I'll have to really define that for you as I go. But the idea is that, if you, for example, had a database and you had a question, then your representation of meaning should be whatever is sufficient such you could take this question, convert it into that meaning, execute it against the database, and get back the answer. Okay, and if you can do that with your representation of meaning, then we'll call that some notion of a complete representation of meaning. All right, although in general, all these terms are a bit up in the air and fun to discuss if anybody's interested. Now, before I move on, I should just say I think even though there's work all across this spectrum, our goal is all the same, right? The people that are broad coverage are trying to push deeper. The people that are deeper are trying to push broad coverage. And our real dream is to get a full semantics for every possible sentence you could possibly consider. But trust me, we're not there yet. So it'll be fun to see where we are, and we can discuss that as we go. Okay? So some examples of what I'll be looking at. When I talk about mapping sentences to meaning, I'll think of a sentence and a logical expression of its meaning. So it'll be a lambda calculus expression, but here's one simple example. So if I made the claim Texas borders Kansas, okay, this is just a simple sentence. It's going to either be true or false in a particular setting or a particular database. It would map to something like this. You would test some relation between two entities, right? And in a particular database, you could look up these two entities, you could look up the relation, and then you would know whether that sentence was true or false. All right? A lot of the sentences I'll talk about today are actually question sentences. So to represent the meaning of questions, it's a little bit more complicated. So if I had the question for a geography database, what states border Texas, then the meaning that I would represent is some sort of lambda function, right? And this lambda function is an implicit representation of a set, because it's going to represent the set of things that are the answer to the question, right? And the way we do that is because we have this variable here, and so for each thing that could possibly be in the set, we can substitute it for x. We can test whether this property holds, whether this other property holds, and exactly the set of things that return true from those tests will be the things in the set, and those will be the answers to the question. Okay? So this is the basic setup. We've got this notion of using lambda calculus for meaning. We've got this notion of sentences. And now we're going to phrase a machine learning problem. So what we're going to assume access to for most of the talk, although we'll come back and revise this towards the later part, is a whole bunch of examples of input-output pairs, right? So if I gave you a whole ton of these sentences matched with their meanings, what could you do with that? What could you learn to do? Could you learn to analyze language? Could you build a so-called semantic parser out of that? Okay, and that's the basic setup for the talk today. And just to get a feel, although we are limited domain, we're going to be able to do all kinds of complex stuff. So we'll have quantifiers like what is the largest, where we have this argmax construction over some set of things, comparing each according to some property. Similarly, we'll have nested constructions, so what states border the largest, and these things can get kind of arbitrarily complex. So what states, the border, blah, 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 where you have some string of quantifiers, and you have to scope things correctly to actually get out the correct interpretation that there should be a chain of these relationships up to a certain length. Okay? So any questions about the basic setup? what we really have to do here is think about how are we going to phrase this as a learning problem, and what would you have to do with data, and what could you assume to be able to actually learn well in this setting. So, the first thing you might say is, well, if you're going to learn this thing, what we're actually going to have to do is go through all of our data and do some full annotation of all of the steps that are required to do the analysis. So if somebody gave you data that looked like this, you could use sort of standard off-the-shelf supervised learning techniques, right? And don't try to decipher this tree yet. Later on, I'll take you through some of the details of trees like this. But the key idea is that there's some representation of meanings for words and phrases and various ways of combining them to get out some meaning at the end that's actually for the full sentence, right? But, if you actually had to do this for a bunch of data to train, this would just be prohibitively expensive, right? We're not going to go and do this, right? So we'd like to be able to learn from less. We'd like to be able to learn with as little annotation effort as possible. So what if we only required the final meaning? So what if we only had this, we had the sentence, and all of these decisions in between were latent? So we try to reconstruct all of those. And so this is a pretty standard setup that's been addressed over the last, say, 5 to 10 years in this research area. And I think we've pretty much got it, for large classes of problems, we're doing really well in this kind of a setup, right? So I'll take you through sort of the latest version of how to do it and how to learn where all of this is latent. But one really exciting thing, at least from my perspective in this area, that's been happening over the last year or two is people have been going even further. So we've been saying, well, actually, what if we didn't even have that, right? So what if you just had the sentence and no lambda calculus? Because, of course, annotating lambda calculus is a pain also, right? It's not easy. Well, this seems too magical, right? It's just text with nothing else. It turns out you'll have to actually shove in some other things. So we'll have to do something else to get some sort of leverage. But this is kind of a current research area that we'll come back and talk about a little bit. One approach that we have for doing this, and there are other approaches in the literature. Okay? So just to give you a feel, this is what I was talking about. The so-called supervised case here is the latent variable case that I was talking about that has had most of the work recently. And then there have been all these, just in the last year or two, variations where even not annotating the logical form, but doing even less. Okay? So that's the basic setup. What I want to do to take you through is to take you through two algorithms. And before I can do that, I'll have to do a little bit of review of CCG and how we do semantic parsing in this formalism. And then I'll talk about two specific cases. So one is where we're doing the hidden variable learning with the language and representation independence. So we'll be able to learn for lots of different languages, lots of different representations of meaning. And a second is where we actually don't have to do any annotation of lambda calculus at all, but we're actually able to learn instead in the context of a conversation. So you're actually looking at a conversational trace, and you're able to induce semantic parsers based on how the conversation went without having to do any hand labeling at all. Okay, so that's basically where we're going. All right, so straight into it. Parsing with CCGs. So what I'm showing you here is a parse tree. And the key idea is that we're annotating something on the words and phrases, and we're combining them together. And if we can do this parse, what we'll get out at the end is some syntactic thing, which is an S, and has the particular lambda calculus expression that's the meaning that we're trying to produce. Right? And to be able to do this kind of analysis in this sort of formalism, which we would call a heavily lexicalized formalism, there's a really cool way of thinking about it, which is that almost all of the decisions come up here when we're choosing what to put on each word. And then there's a relatively few ways of combining things. So let's just walk through that here, and we'll see later why this is really useful for doing grammar induction. So for example, what we're going to do is just name a few things so we have the notation. So the lexicon is the way that we represent the meanings of the different words. Each lexical entry has some text, where I've highlighted the text here, in a category, where the category is now highlighted. So that it's going to have syntactic and semantic information. And the category is further broken apart into syntax, which are these non-terminals and slash. We'll go through a little bit exactly what the slashes mean, but they're basically encoding word order. And then it's also going to have the lambda calculus to represent the meanings of the individual words and phrases. Right? And then the idea is that to do parsing, so you see the result of a parse here, but the way we knew to do these parse steps is by looking at the syntax and using that to guide the steps. So you can, for example, look at this right slash here and say, I'm looking to the right for an NP. And there's actually an NP there, so I can combine these two to produce the result. Okay? And similarly, when you put these together, you can actually do the lambda calculus combination. So what we did here is just substitute Denver for this first argument, and we get out the result. And you can have a relatively few set of possible steps like this. So here we use what's called the application combinator. There are 4 or 5 different combinators that describe how to take 2 categories and combine them to get a new one. And then in general, we just have to get what are the lexical items, and which order should we apply the relatively few combinators in. And those are going to be our choices for how to do parsing. Okay? Are there any questions about this setup here? I'm not going to go through it too much more, but we're going to see lots of examples of these things as we go through the rest of the talk. Sort of a lightning fast review of CCG.
I guess just one question. So we look at the word form, the from.
Yes?
So that the thing in the lambda expression, which is also called from.
That's right.
Now, I shouldn't necessarily think that it's the same as the lexical, right? You want that to be something.
That's a great point. That's a great question. So these symbols in a database application, for example, would come from your database schema. And they could be arbitrary symbols, and that's just whatever happened to be in the database. And we're going to learn from database queries where these symbols are basically the symbols in the database, and they have absolutely no relationship to what the text string is. So you'll see later I'm going to change this text string to be Turkish, and I'll use the same symbols. It doesn't matter. And we're just going to learn the correspondence, and we're going to learn the grammar so that you actually get out the right analysis. So the reason I've left it like this for now is just because it's easier, but it's a really great point that you bring that up.
Okay, and then how much are you going to assume is known about the lexicon? I mean, the lexical entry. I guess you're going to learn
We're going to learn the whole thing, and I'll show you. That's the first half of the talk. That's the key, is learning the lexicon. That's the key challenge. And then there's the issue of a probabilistic parsing model, too, and we'll do that, too. But this is the structure challenge of what we're going to do. Are there other questions? OK, great.
So actually, just you don't learn any lexical redundancy rules. Is there any structure in the lexicon?
There is, actually. That's our most recent paper. So I have 2 slides on that.
Fantastic.
OK, yeah. OK, cool. So in general, when you're doing this kind of parsing, as we just said, you could have multiple meanings for each of the words. So this might not be the only meaning for from. You know, maybe New York is actually both a city and a state, right? So we'll have lexical ambiguity. And then we'll also have ambiguity, like everybody knows about in parsing, about how to combine things, right? So in general, we're going to need a probabilistic parsing model where we can weigh off the different possible analyses. And we're not going to do anything too fancy here, but I just want to set up the notation, which is that we have this idea of a lexicon, this list of word, syntax, semantic pairs, some parameter vector in R to the n, and then, OK, you should be totally shocked. We're doing a log linear model, right? Never seen one of these before, right? So we're building on top of standard machinery. We have this notion of, for a sentence and the output logical form y, the latent parse tree that was actually used to build it. So sentence, parse, logical form, x, y, z. And in general, if you're trying to predict a logical form for some input sentence, you can really just you can marginalize overall possible parses that could build it. You can actually also put a max there. It doesn't tend to make much of a difference in practice. So we're not being terribly philosophical about this. And actually, in this talk, I'm not even going to tell you much about these features. I assume people know a lot about features. We're using pretty standard parse features. We at least have indicator features on the lexical items to learn which ones are good and bad. And that's pretty much all I really want to say about features, unless somebody wants to super quiz me about them later. They are pre-specified, and they will be part of the probabilistic model. But the key challenge is inducing lambda for us. Okay? So now we're ready to start thinking about how we actually learn these things. Okay, and this most recent result, so this was work that we did with Tom Kwiatkowski, Mark Steeman, and Sharon Goldwater in Edinburgh while I was there, and then it continued on into the last year. And before this, a lot of the work that I had done was really specific to English, and it was very carefully crafted, and it was always a little bit unsatisfying. So what we did here is we sort of asked the question, how general can we make these algorithms? Could we learn for any language if you had the data, right? So what we're going to assume is that we have a bunch of pairs of sentences and meaning representations. Okay, and each data set is one language, right, and one particular way of representing meaning. And then we have many different data sets. So if you took your English data set and you just translated all the sentences into Turkish, you should also be able to learn on that data, right, using the same meaning representations. Now, it's sort of, this is perhaps questionable exactly how to represent meaning, but at least then you could execute those things and get back reasonable queries. Right, so that's the basic setup of what we're doing here. And we'll come up with a general way of doing it, and we'll evaluate it on lots of different languages.
You have the lambda expression for one language, and you translate it into another?
Just translate. So the way that so we actually gather data in English, and we'll get into this more when we do the evaluation. And then you just go through and translate all the sentences to get data in other languages. So you get new data sets that way. Okay?
But then how do you infer the meaning?
So you use the same meaning. So the words will change, but you use the same symbols. Because the meaning is labeled here. Okay? Okay. So that's the setup. And the style of learning we're going to do, so I'll give you a schematic of the learning, and then we'll break into the different steps, right? But the style of learning we're going to be doing is this online interactive style of learning. So we're going to start out with some initial model, and I'll have to carefully tell you how we start things up. And then we're going to iterate through the data in an online manner. So we're going to take each training example one at a time. And that training example is a pair of a sentence and its meaning. And we're going to do some amount of things. So we're going to sort of look at that example. We're going to say, oh, are we getting this example right? Well, okay, if we're getting it right, we won't make many changes. If we're getting it wrong, there's sort of two things that could have gone wrong. You know, maybe something was wrong with the lexicon and we need to update it. Or maybe we actually had the right lexicon, but our probabilistic parsing model wasn't able to pull out the right parse given that set of parses, right? So we sort of have these two different cases that we have to deal with while learning. And I'm going to first talk a lot about some background that we're going to need to understand how to add items to the CCG lexicon. And then I'll come back and show you how it all fits together with sort of a trace of the algorithm running. All right, so we'll get a feel for what this style of learning actually works. But let's dive into a little bit about the lexicon. So how would you start up a lexicon like this? So, you know, what we said was, well, we don't really know what the individual words should mean, but we're going to allow lexicons with whole phrases in them, right? And so we said, well, one way to start this thing up would say, okay, I'm going to take every sentence in my corpus. I'm going to say syntactically that sentence is an S, and I'm going to say it has the meaning that was actually labeled for that full sentence. Okay, so that will start things up. And the question is, how well is that going to do? So training error. So pretty good, right? 0 training error. How about test error? Probably 100 or something, right? This is just silly. But it gives us the intuition that we have some lexicon that's representing our data. But what we really need to do in order to have any hope of generalizing is start thinking about smaller phrases, right? So we need to take these bigger phrases and break them into smaller phrases. And so we're going to set up this notion of splitting lexical items. So if we took that original entry and we split it into these two entries, so sort of what states, where this is something that's looking for this guy that we split out, and it's sort of just got the state left. And then we've got this other one, borders Texas, where we pulled out this whole sub-expression, right? So we're sort of take this big thing and start breaking it into pieces. This will give us some hope, right? So we'll be able to then maybe, if these whole phrases appeared in the test set, but in different combinations, we might be able to recombine things, right? And of course, we wouldn't want to just split once. We'd want to split, you know, many times. And we'll get to that eventually. That will be the overall learning algorithm. But what we want to do first is define for you a space of possible splits so we get some feel for what the branching factor of this learning process is going to be, right? And I have to stress that, you know, this was obvious we should do this split here. This is the point about the symbols being in English. But of course, whatever the algorithm is, it should also run reasonably on Turkish, right? So do we have any Turkish speakers? Because I have to apologize in advance. All the examples, they're like, the splits are all wrong and stuff. But that's because it's from an actual algorithm running. So you can sort of laugh and tell us what's going on there. But when I trace the algorithm, I trace it in Turkish so that we're all equal, you know, everybody except for you are at a disadvantage and don't know what's going on. And you can sort of snicker a little bit. Okay, so we'll get into that later. But the idea is that it would run on any language and hopefully do well. All right? And the way that splitting is going to work is there are going to really be 3 parts. So we're going to have to take the meaning, the logical form, and split it into 2 pieces, right? And then given these new pieces of meaning, we're going to have to work out syntactically what's going on. So for example, if I put one of them to the right and one of them to the left, I need to make sure that slash matches up so that we can recreate things, right? And once I've worked out the meaning and the syntax, I also have to work out what to do with the sentence, which is that if I had this long phrase, I need to break it somewhere, right? So I need to decide meaning, slashes, where to break things, right? And what I'm going to do for now is define a huge, overly general process. So this is going to be sort of the space of all possible splits. And then later on, we're going to have to be intelligent about not just enumerating all the splits, but actually finding the right single one to do, where we have some notion of noise and some ability to recover if we make mistakes, right? But let's first just think about this huge space of possibilities. So to do that, I'll start with number 3. What's every possible reasonable split of a phrase? It's just every breakpoint, right? So when we define our space of possible splits, we're going to just allow for every possible breakpoint in the current phrase. And then the trick of this, so once we've got that, I want to tell you a little bit more about 1 and 2 in detail on some slides. And the trick really in getting this whole thing to work is to control 1, because it can get really out of hand. So the question here, and this is this notion that we sort of talk about in the paper and build upon from previous work, is this notion of higher order unification. Okay? So a higher order unification problem. So how many people know unification from, say, first order logic or something like that? Okay, so that's helpful. But the basic idea is that it's a way of solving for unknown variables in logical expressions. So what I'm saying is that I've got some input h, which is my original thing I need to split. That's also up here. And I say, find me all pairs f and g, such that, so for example, this would be f and this would be g, such that when they're recombined, either according to function application or function composition, they'll recreate the original h. Okay? Now, the reason we do application and composition is because those are the two basic operations of CCG parsing. So what we're basically saying is, like, the CCG parser goes bottom up and builds things. Let's see if we can enumerate every possible way of splitting apart into anything that could then be recombined to create the original result, right? So we're just sort of algorithmically undoing things, right? But there's one hitch here. These problems are actually undecidable, okay? So it's a minor detail. So what we had to actually do was restrict things. So you can go look at the paper, and we have this sort of list of cases that we thought, oh, these look reasonable. These are sort of linguistically okay, we hope. And we had to say, you can't do this, you can't do this, you can't do this. And therefore, we can get polynomially mini splits. It's still going to be big, but it's not going to get totally out of control.
Is it undecidable for the typed lambda calculus?
Yeah. I believe that's right. And actually, it turns out this is actually decidable because this is matching and not full unification. So I should be a little bit careful and just say it's really hard and not be so formal about this. Because actually, we're doing a special subcase. We're not doing the full really hard problem. Yeah. We also have types in our lambda calculus. I'm just not showing them carefully here.
Right, that's why.
Yeah,
I mean,
yeah.
those are attached to the syntactic calculus.
Right. Right. All the symbols are typed. Okay, good. So then with this notion, we have this idea of sort of doing all the possible splits. And we had to do a little bit of empirical tweaking, but we're building on this nice mechanism. So we have at least some idea of how close we're getting to the space of possible splits. Okay?
Is there a matching between what kind of split you do with the lambda expression and what kind of split you do in the CCG category?
Yes, and that's the next slide. So good. So now let's assume that we've done a split on the lambda expression. So we originally had this CCG category, say this one here, x with meaning, the original full meaning, and we split it into f and g, right? So now the question is, how do we fill in the rest of this stuff so that we can parse and get back to x, right? So we're missing some stuff here. And what's actually missing? Well, we need to decide whether f is going to be on the left or the right, and g are going to be on the left or the right. So we have these two pieces. Do they go this way, or do they go this way? And I'm only showing one option here. But we would do both in general, right? When we're doing the space of all possible splits, we would allow for both possibilities. And then once we decide what order to put them in, we need to recreate the slashes, right? So we need to have the slashes such that this parsing operation can actually do it. Well, given the left or the right, one of the slashes is determined, right? Because we chose the order, so we have to be able to at least take that argument that we just split out. But it turns out there's a big unknown, which is what to do with this syntax here. Right? Do you start inventing new symbols? What do you do, right? So we need some way of syntactically naming this new expression g that we just got out, right? Sometimes it seems relatively easy. So for example, for this split, we pulled out just this single logical constant. We kind of know that should be a noun phrase, right? That's just sort of how we usually do things in these semantic representations. These things are entities. Noun phrases are entities, right? But in general, how do we go about doing this, and what's a reasonable naming scheme? It turns out that what we decided to do is there's sort of no perfect solution here. But we came up with a simple scheme that didn't require inventing any new symbols. So what we do is we take the type of the lambda calculus expression, and we say, OK, based on what type of lambda calculus expression, we're going to have a deterministic procedure for determining what to call it. So the syntactic names are going to actually match the semantic types. So for example, if it's an entity, we'll call it a noun phrase. If it has a truth value, something that can be either true or false, we'll just call it a sentence, okay? Because sentences usually have true or false, okay? And then we're going to do this recursively. So anytime there's a functional type, we're going to recurse down and just make these sort of named things with these vertical slashes, which are a little bit of wildcards that can actually be these compositional things, okay? So one place where this is slightly strange is that, this expression here, for example, is typically sort of an intransitive verb, and you'd actually expect to see a left slash. So we don't always get all the slash orders correctly, but you get sort of roughly the right structure on these things in terms of what you would expect to see in a categorical grammar. Okay? So the key story here, even if the details are a bit opaque because of the typing, is that we have a nice deterministic way of doing this, and we don't get an exponential blow up in slash directions. Okay? So that's the basic story about how to do splitting. So what happens when you actually run this? Okay, so here are the splits. Then it goes on and on, actually. Here's a subset of the possible splits for this original motivating sentence. Right? And what do we think about this? Well, it's got some crazy stuff in there, right? So it's got some good things. So for example, here is Texas meaning Texas. But up here we've got Texas meaning next to Texas. And then up here we're going to have Texas meaning state. Right? So this just got all kinds of crazy stuff in there. But the key idea is if we've defined the procedure well enough, there should be the correct stuff too, right? So we believe that we've been general enough that for all the different languages and all the different ways, we'll be able to get the right pair. But now we just need to say, how are we going to actually select that one, right? How are we going to filter through all this madness and get out the right solution? And then how are we going to do that recursively? So not just once, but repeatedly as we analyze sentences. Okay, so that's where we are now in terms of the challenge of this algorithm. All right? And how do we do it? So back to the algorithm. We're going to have this iterative online thing. So this splitting is going to be somehow used here. And then the results of updating the lexicon are going to change the space of possible models under our parsing model so that we can update the parameters after that. And we're going to iterate this back and forth. Okay? And so far, it's not exactly clear how this is going to go. And you just have to hang with me for one more slide, because before you see how it fits together, I need to tell you a little bit of how we're going to initialize things. So it's just really hard to do this splitting with no careful initializations. So what we actually did was we took all of our data and we ran IBM Model 1 alignments. So we took the symbols and just treated them as if they were words. Model 1 has uniform distribution, so we're not using any kind of word order here. We're just looking at co-occurrence between words and symbols across the whole corpus. And we compute pairwise scores. So for any particular pair, so this symbol with this word versus this symbol with this word, we get some rough, noisy score for how likely they are to want to be with each other. Okay? And then anytime we create a new lexical item, we're going to give it an initial lexical weight on its feature for the lexical selection. That's the average of the pairwise scores across the whole entry. Okay? So that's how we're going to start it up.
So it doesn't take into consideration like reorderings or initializes. Have you tried looking into that? Like, I wonder how often.
Right. So there's this interesting trick, which is that order is not really relevant for lambda calculus. So it actually would be bad to have an order-sensitive model. Because, for example, if I switch these two, it's a conjunction. It doesn't change the meaning at all. So, but it's a really good point. I suspect if you were careful, sometimes order does matter. Like here, you could come up with some cool hybrid thing where you paid attention to order where it matters and you don't where it doesn't matter. But we've just kind of stayed away from that. It's a really good, interesting question. Anything else while we're here? Okay. So, go ahead.
But IBM Model 1, so I thought that IBM Model 1 took advantage of order, or assumed a certain...
So there is an ordering component to it, but you assume uniform distribution over all possible orderings.
Okay.
Yeah, so that's the sense in which the order doesn't matter. Okay, great questions. Okay, thank you. So now we're going to actually, rather than going through all the formal details, we're just going to trace this thing running, and that will give us the intuitions for what actually happens in practice, right? So what happens in practice? And then, here's where I'm starting to butcher Turkish sentences, okay? So what happens is, well, the first time you see a sentence, this is going to be your parse, right? It's guaranteed. This is the only thing you have in your lexicon, is these big, full lexical item with the S and the meaning. Okay, so, well, our first step is to find the highest scoring correct parse. You're guaranteed that that will be it, right? And now your second step is going to be to find a split of some node in that tree, if any, that increases the overall score of the analysis. Okay, so in this particular case, we might do a split like this. So I've actually left Texas in English here, so I said, okay, well, I'll just pull that out. That seems pretty reasonable. They probably have a high initial score according to that co-occurrence, and then we'll leave all this other stuff over here, right? And I think what's actually going on here is actually a mistake, so I think this should come along. But anyways, the point is the algorithm can make mistakes. It's okay. We'll sort that out later. But for now, we're just considering some sort of reasonable split. Okay? And so then after you find that single best split, if there is one, you add up to 2 new lexical items, right? Because you have these 2 new things you've done. So you're really controlling the amount of splitting that you're doing. You add those into the lexicon, and you update the parameters. So what is updating the parameters? Well, we have this log linear model. There's a well-defined notion of stochastic gradient. So if you just differentiate the likelihood for this one example, you'll get this standard stochastic gradient update. What's going on here is that we have a positive update on all of the parsers in expectation that produce the labeled output semantics. And we have a negative update in expectation on all parsers that are unconstrained. So importantly, parsers that get bad results are going to be in this negative part of the update. And parsers that get only good results will be here and will push up the features associated with the good analyses, push down the features associated with the bad analyses. And in particular, we'll also do that for the lexical items. So if we had learned some bad lexical item along the way, its weight will get pushed down. And because we're always doing max parsers all over the place in this algorithm, it'll eventually stop getting used, and you'll consider different splits and different ways of reanalyzing things. So just sort of run this process iteratively like that. Okay? And pushing along, we would repeat. So you'd find the highest scoring correct parse. You would split some more. And then this procedure just kind of keeps running like that. Okay, so any questions about the procedure? That's basically all I'm going to go through.
So what do you, why do you need the CCG category here to guide you how to do function application and computation?
So by category, do you mean just the syntax part, or do you mean the whole thing? So it's clear you need the lambda calculus, right?
Yeah.
That's right. So this is what encodes word order. Encodes word order. So you could try to do a semantic parsing algorithm without word order. But for example, if you had a transitive verb, how would you know which direction you should look for the object and which you should look for the subject? That's encoded in the slash order.
So in particular, once you've gotten this will constrain the parsers that you're willing to consider for the next sentence that you're looking at. Right?
Absolutely. Yeah, absolutely.
Well, if you look at all the last two branch nodes, just from the lambda calculus, can you tell which direction you should apply?
That's right.
From here, it's like seeing the first one takes an f, which is a function. So definitely the first one is a function, the second one is argument. It's not going to be the argument.
In this sentence, the typing is such that there's only one way to put them back together. Yeah. And that will not generally be the case. So I just haven't shown you the right sentence for your question. But just think about a verb taking two noun phrases, one to the left and one to the right. And then hopefully it becomes clear. Just think of that simple declarative sentence. Okay, that's a great question. All right. So some experiments. We evaluated on these small data sets. This is a standard benchmark in English only. Some subset have been translated into Spanish, Turkish, and Japanese. We'll see how we do there. I didn't talk much about meaning representations, but basically any logical meaning representation that you can do splitting on, you can run this procedure on, right? So it turns out there's this so-called Funkel representation that existed in the literature. We just kind of grabbed that, and we run on that too. And here these are sort of functions from sets to sets. And I don't want to go into too much detail, but we're sort of somewhat ambivalent about what the representation is as long as we can define how to do these splitting. Okay? And how does this actually work? So here's a set of results. So this is accuracy, percent of fully correct logical forms. So what percent of the sentences do we get absolutely, completely correct? So this is a really tough metric, right? And, of course, the data is limited domain, and so we can do quite well here. In terms of the comparison systems, some of these are not directly comparable. So this is on English only, right? So this is the 880 data set. And these two were my thesis work, and they only ran on English. And they had a huge amount of language-specific knowledge built into them about how English works, right? And we were sort of shocked to actually see this guy come out over here. We kind of say, oh, maybe if we don't do even as well, we can sort of close the gap, it would be okay. But we were actually able to beat it. We were sort of surprised by that. This is a relatively small data set. And you'll see on a bigger data set, this actually doesn't quite turn out the same. And then this was in the different meaning representation. And we sort of compared to all the reasonable state-of-the-art stuff, right? Across languages, we see the same trend. So here, this is our algorithm, the UBL algorithm. I should have said unification-based learner. And we're consistently beating all of the previous algorithms on all the different languages, although there is some variation in performance. Some languages are a bit harder than others, okay, across the overall setup. And in particular, you see Turkish is pretty hard there. It's got a relatively free word order and a relatively rich morphology, both of which we don't handle terribly well in categorical grammars.
And sorry, where do you get these data sets from? You take the English geo set and you translate into Turkish? Did you guys do the translation?
Somebody in Texas did. I didn't actually do it, but I'm not sure who did it.
Somebody next to you.
Yeah. Somebody who lives in Texas that I do not know. Okay, and so here's a rough idea of some of the things that get learned. So, for these different languages, we're seeing these sort of consistent trends. English actually makes sense. You get these most quantifiers, states and borders. Spanish I can almost make a little bit of sense of, although I'm not at all bilingual. Estado, that's probably right. This is some sort of argmin construction, right? Something that's some sort of smallest or something. And so we're getting these pretty consistent trends. And you're seeing sort of the same things coming out, but you're seeing the syntactic variation across languages with the same kind of semantic constructs. All right? So that's sort of the end of this first piece. And I will just do a very quick vignette of an extension to this, but I can't possibly go through the details. But I just want to show you one issue that comes up with this style of learning.
How did you choose these lexicology?
These are the highest scoring under the weights. But, it's sort of lucky that they looked so good. I mean, there's no really reason to believe that would necessarily be the case. It's a great question.
Maybe the highest scoring ones are in that corner, if you're correct.
I guess it's also an issue of frequency, right? Because we're doing the stochastic likelihood. But yeah, that's probably true. And there is garbage in there, don't get me wrong. There's a lot of stuff in there. No, I would say no. I would say that we're consistently doing better. So if we did some sort of meta average thing, we're probably better. But these are small data sets. So I would think that probably not. Okay. So let's push along. So what's a challenge that comes up? So one cool thing about this learning now is that we can sort of handle anything, right? So we can handle arbitrary stuff. And in particular, we can actually even handle ungrammatical sentences, right? We don't label syntax. So we can deal with all kinds of different settings. And there's a bigger data set, which is the ATIS data set, which is actually spoken flight travel queries. And in this data, there's all kinds of weird stuff. People are saying weird things. They're saying ungrammatical things. They're dropping words. And it's just sort of much harder and much bigger than the previous data. And we say, well, we should be able to run on that, right? So if we're doing this learning and it's completely independent, let's just run and see what happens. And so we sort of get this, for example, phrases, flights Boston, New York, right? And so you sort of know, well, there should be a from and a to, but those weren't exactly said. Well, we can learn to analyze that. You would get something like this. But in general, to do this kind of analysis across all the different ways you could say Boston, New York flights, flights Boston, New York, flights Boston to New York, flights from Boston, New York. You see they sort of have this all possible permutations, all different ways you can drop words. And what happens is you get this huge explosion of different meanings for Boston. So Boston could just be this noun phrase. It could be what you do when it comes after and the word from is missing, when it comes after and the word to is missing, when it comes before and the word missing, before, after, and then all these other type phrase variations of these things. Okay? So what's happening is that we were having to learn over and over and over again, say 10 or 20 times, basically syntactic variations on things that are very closely related to this common semantic themes throughout. Okay, so this was really causing a sparsity problem in the learning. And so what we did is introduce this notion of a factored lexicon. So this idea that Jason was sort of, it's probably not the same idea, but at least some structure on the lexicon. And the key idea is learn the word, learn the key semantic symbols that should go with it, call that what we'll call a lexeme. That's sort of the core of the meaning. And then learn transformations that, or templates that map that semantics and fill in the rest of the syntax and the other part of the semantics that can actually vary. Okay? And so if you start doing this kind of learning, now you can learn from much less supervision, right? So you can get some sort of feel for how to do this learning where you can really get by. Even if you saw every possible, Boston, New York, and a bunch of other cities, and each of them were only used in one of these situations, if you do the factoring, you can get the whole cross product out and actually do the learning.
We read this paper, and we had a question on, by using this device, do you still call CCG under this framework fully lexicalized?
Fully lexicalized. What does it mean to be fully lexicalized? I mean, all you're going to do is change your derivation after you do this so that you have sort of two choices to build a lexical item, right? So I would call it fully lexicalized. I think of this, I mean, we have to define terminology, but I think of this as a compactness issue of the lexicon, right? So now there's this huge lexicon that we've implicitly learned, but we've learned it and represented it in a much more compact way. So that's the way I think of it. But you could probably make an argument the other direction, too.
So I have a follow-up question, but I mean, the earliest days of lexicalized grammars like LFG had lexical redundancy rules. And in trade joining grammar, there were tree families. And, I mean, all these things need that because otherwise you wouldn't be able to conjugate a new word having seen it once. But,
right.
Well, I'm saying that more for other people than what are you doing with the probabilities at this point?
So we're just...
Are probabilities completely factored also?
Yeah, so we're going to have features that look at the different factored parts, and then we just make 2 steps here in your to get your lexicon, 2 steps in the parse tree. It's basically just another non-terminal, and it runs just like normal.
Yeah, okay. I mean, that does to some extent undercut the notion of it being fully lexicalized, and that you would like to be able to learn some of these, you know.
Oh, we have the pairwise features too. We have the pairwise features too. Yeah, yeah. Okay, okay. Yeah, good. So that's if we didn't do that, then that would definitely be a problem. That's right. That's right. Good. Okay, so I need to push on because we're running short on time, and I haven't even got to the conversation stuff at all. So we'll kind of fly through that when we get there. It'll be fun. One cool thing is that I won't go through the details, but actually you can basically directly update the previous learning algorithm. So instead of just directly sticking in lexical items, I have these 2 ways of tweaking it, and I need to basically take those lexical items and factor them into these 2 pieces. And I would just claim that it's not too hard to do that change, right? So we can just update this online thing to be able to add factorings in different ways, and then we'll be able to do the learning, but I can't possibly tell you about the details here today. So you have to go look at the paper for that. Okay, so we did an evaluation with the full credit like before. And here we also did a partial credit thing. So if you get some of the attributes right and not others, then you can actually get some partial credit, right? And here's what the results look like on this much bigger data set. And you see that here we sort of didn't quite get back up to the level of this carefully English-crafted system. We're here in the middle, but we solved a lot of the sparsity from the first part of the talk. So we're able to close a lot of the gap and really do a lot better in general in this performance. Okay? And this is, in my opinion, a much more challenging task than the original ones. Okay? And here's some examples of the types of things that are learned. So you get sort of these noun phrase type things, these things that are sort of roughly defining sets and properties, and you get these quantifiers. And one cool thing is, after is a greater than according to departure time and so forth like that. And then the actual details of the syntax and so forth get filled in with these much more complex constructions. Okay? So that will end our fully supervised thing. And let's make sure we have some time at least to get through some of the intuitions of the conversational stuff, even if we don't get through the whole thing. Okay? So what's going on here now? I'm making a big switch. So I want to talk about semantics in the context of dialogue and conversations. So what I want to do here is say, imagine that you wanted to have a conversation like this. There would be many different components of this system, but at least one of the components would be something that takes these individual sentences that the user is saying and maps them to some sort of logical representation of their meaning. But here the logical representation would be used by the dialogue planner to then forward the conversation, right, to help you make progress. And I'll tell you about a particular type of learning exactly those same sort of parsers for some sub-part of this problem, right? And in particular, we're going to look at sort of analyzing sentences that are sort of in the beginning, and or they can be in the middle of the conversation too, but they have a notion of a context-independent meaning. So these are sentences that could stand on their own in general. Right? And so the thing you might want to have in mind here is imagine you come to the system and says, how can I help you? And then you being new to dialogue systems, are going to just give this really horribly complex query. Right? You're going to like just list everything out. It's like basically this paragraph of text. And then you know what's going to happen, right? So the dialogue system is not going to have any hope. It's going to fail. And then it's going to say, leaving what city? And then the user is going to be like, oh, right, it's going to be awful. And then you'll say, oh, actually, leaving Atlanta. Okay? And the interesting thing is, although there was some sort of parse failure, we weren't able to do anything with this. We start this remediation strategy, and now we start to get some clues about what this original thing might have meant. Right? So we're getting some feedback there. And say, oh, maybe we'll confirm that. Okay, leaving Atlanta, great. Where are you going? London. Oh, good. Okay, we have another clue. We might confirm that. We'll go on, and we'll keep getting more and more clues. Okay? So the idea is that if we think of this as a learning problem, we can actually say, well, can we use this sort of recovery mechanism to automatically improve a semantic parser so that if we ever saw a sentence like this again, we wouldn't make that same mistake. Right? And that's what I'll tell you about a little bit here. And it'll be cool. We won't have to label any logical forms to actually do this. You can do this in completely without any annotation effort. Okay? And the key thing here, though, is that we're still going to learn this same function. So this is why I can kind of glom it on the end of the previous talk. We're still going to take sentences, put it through the semantic parsing function, and get out exactly these kinds of meanings. Okay? And the key contrast that I want to make is to the supervised case. So that's what we saw before. The supervised case, you said you had to have a sentence. You had to have the logical form labeled. And the cool trick that we're going to pull is we're going to introduce a notion of loss. So what this notion of loss is going to be for any particular z, any possible meaning for this sentence, and a particular conversation C in which this sentence was used, it's going to give us some real number, some indication based on that conversation how likely was this sentence to have this meaning? And then we're just going to rejig our learning. So instead of saying, did we get it right or wrong, we're going to be a little bit sensitive to this loss. And we're going to use this loss to drive the whole framework. Okay? So in particular, we're going to have to think about lots of different possible meanings for it. We're going to assign a score to each. Because it's loss, we're going to want to minimize loss. And we'll say, OK, well, actually, this is the right one that we need to get. And that's the setup. And I need to talk you through how we actually do that. OK? And the way we're going to do this is we're going to actually have a little bit more structure than just the text. So we're going to assume that the conversations were between a system and a user. And because they were between a system and a user, we can log some representation of the meaning of what the system said, at least the meaning it intended to convey. Right? So we can actually have logs that look roughly like this, where in this log we have a bunch of system utterances and user utterances. And for each system utterance, we log representations of what was going on. So we've got the natural language of what was said. We've got some representation of the speech act. So is the system intending to confirm something? Is it intending to ask a new question and so forth? There are about 6 or 8 of these possible speech acts. And then we have some representation of the logical meaning in terms of what was actually being asked. Right? And this is just the same kind of lambda calculus expression we've seen before. And finally, we're going to keep track of some notion of conversational objects. So which flight, if there's some long list of flights you're discussing, did the system think we were actually talking about right now? So we have this notion of these objects that spread across the different utterances, right? And this is what we'll actually use. So the cool thing here is that we don't have to induce it all from text. We get some logical expressions to help with inducing other logical expressions. That's good. We get those for free because we're compiling them out of the system. And this is what the system intended to do. Okay? And the key idea, remember, of course, is that we're going to have this one training example. So this whole thing is one single training example. We're just working on analyzing this sentence. And later we'll get into doing, future work is going to be doing learning for full dialogue systems. And we're just looking at this one case here. And the idea is we're going to have some conversational logs come in. We're going to seed this thing with a lexicon. We're going to tell you the details of this loss function that I described later for how to do the learning. But then the output is going to be the exact same output as before, a much bigger lexicon where we've learned more thing and parsing parameters for how to actually do the parsing. Okay, so we're exactly in the same setup, but we're just getting rid of the labeling. Right? And the loss function breaks into 2 parts. You can look at the paper. There's some small amount of domain-specific information about flights that really helps a lot. Sort of knowing roughly, it's sort of like a language model over logical forms that you might expect to see, but it's very rough. And then most of the feedback is actually coming from the context of the conversation. Right? And here's how it goes. So I'm just going to give you a 3-slide schematic. I cannot possibly take you through all the details here. But the idea is you had this failure, and you need to sort of identify what things should we pay attention to, and which one of those are going to actually map back onto things in the failure. Now, this is, I think, also a little bit challenging because in any particular conversation, you may have actually failed. Right? So there's no reason to believe that you actually recovered or that you didn't move on to some other topic that could distract you. But we're going to have this notion of this rough alignment, and that in aggregate, we want to design a loss that in aggregate across lots of conversation gives us good signal, although for any particular conversation, it may not be perfect. Right?
So what is the reason of the failure for this example?
Oh, this is just a toy example. Who knows? Maybe it was actually, this was spoken interaction, so it may have actually been the speech system or something.
So
but
type of failure. One is using the speech.
That's right.
The other one is you might not have the meaning form, right?
That's right. That's right. And we haven't perfectly teased that apart, but from our perspective, we're taking this extreme situation where none of the user utterances are labeled at all, okay, across the whole corpus. So we're sort of just showing that this type of learning is possible, and we have yet to deal with the issues of how to properly integrate it into a dialogue system. So this is the first step. Okay, that's a great question.
So that speech act, like confirm, ask, are also annotated.
That's right, because the system knows what it was trying to do. Okay, so let's push on through. So what we have to do is first have some way of identifying some reasonable set of properties from this conversation that we're going to use roughly as a statistic. So we're going to pull out, for example, things that appeared in confirms and other speech acts, and we're going to weight them. So we're going to say, all right, so there was some sort of from thing going on here, some sort of other from, and some other to. And in general, we're going to weight them so that we prefer closer things, unless we see sort of repeated discussion about the same object to where there's maybe some confusion, there was some clarification going on, and then we'll have a little bit higher weight on the last instance, right? So we get this rough idea of sort of, okay, earlier things are probably corrections, but if there was this back and forth, then we need to look a little bit further. And we just have this rough idea of where we expect to see things. We pull them out this way and give them weights, okay? And then for each possible logical expression that we get in, we do a very simple, greedy heuristic alignment of the different pieces onto this stuff that we've extracted. Right? So we sort of say, oh, well, if this thing was a correction, then maybe that potential came from here, and this thing came from here. And without going through the full details of this alignment, we can sort of sum across it and give us some rough score of how well this meaning is mapping onto the things that we actually saw in the conversation. Okay? And then, of course, we'll do that over and over again for different logical expressions, and that will give us our way to trade off the different scores and actually get out the correct meaning. Right? Or we don't know if it's the correct meaning, but it will give us a ranking over the possible meanings, and we'll have to do that over and over again throughout all the data to actually learn a model. Right? So I apologize, I'm going quite fast here, but I hope that at least you can get the intuitions for what's going on. And that's basically what I have to say about the full details. We incorporated this into a learning algorithm. And the learning algorithm is sort of loss-driven. It has these same two steps as the previous learning algorithm. It turns out the lexical generation step works quite differently. This should not be a surprise. We do not have labeled logical forms. Therefore, we cannot start splitting them. But the intuition is the same. We're just sort of expanding out the lexicon in a sort of driven manner. And we actually use the conversation to drive it, but I'm not going to go into the details there. The parameter update we build on top of sort of a loss-driven perceptron. The cool thing is you can sort of take all of your loss. You can take your least loss things, your higher loss things, and you can update your parameters to try to separate them. So the basic idea is that we sort of on the fly are always getting out new meanings as we're changing the lexicon, and we're just trying to push the parameters so that the least loss things actually win. And we do this iterative thing of going back and forth between lexical generation and doing these updates, and that allows us to smooth across the noisiness as we see the different examples. Okay? So that's basically the idea of how it works. And here's some idea. The data sets are not huge, but we sort of have hundreds of examples of these conversations where we're able to isolate these sentences across two different systems from the DARPA communicator, the Lucent system and the BBN system. And these are travel planning dialogues. So just two quick results. We did ablation. We found that the conversation was much more important than the domain in some settings. Some settings it was a little bit closer. But doing both of them really helps a lot, right? And if you take either of them out, it really hurt the performance. If you took them both out, it would sort of go to 0. Those are their two signals for being able to learn. And here are exact match and partial credit in terms of actual F1 scores. So that was ablation. This is how you do on that was ablation on the dev set. This is how we actually did on the held out test set. And you can see we're able to learn pretty reasonable semantic parsers. The numbers are a little bit lower here. Our signals are pretty tough. But we can at least demonstrate that this style of learning is possible, right? So this is sort of, I would argue, a fundamentally new way of thinking about how to induce these semantic parsers that requires no annotation at all. So more than the raw numbers, just the fact that we're learning something reasonable. Okay? So we'll sort of stop there with these contributions. We've looked at sort of the higher order unification-based induction with the labels. We looked at without the labels how to do the conversations. And for the future for me, I want to go into more complicated dialogues, learning more of the dialogues, thinking about how to integrate with speech and doing joint models of speech, how to actually integrate with the world, talk about grounding, and how to talk to robots, right? So how to have these full conversations and how to really build these things out in lots and lots of new directions. But this talk was mostly an algorithmic talk where we saw these contributions. So any questions?
So for the dialogue system, so I don't know. So how dialogue system resolve the failure issue? There's a policy for them to resolve it.
That's right.
And then you are using that policy to be able to learn to
exactly
get the right meaning in the first hand, right?
That's right. Exactly. So the issue is, there's this sort of interesting active learning interaction between how the dialogue system behaves and the signal you have for learning. So imagine a dialogue system actually fails to remediate well. So when there's a failure, everything just kind of goes crazy and you never actually recover. Then you really couldn't do this style of learning, right? And so we picked 2 of the dialogue systems. There's actually more than 2 in the data, but we picked 2 that did a pretty good job of this. So we actually had signal for learning. I think an exciting direction for the future is to actually think more carefully about the full system integration. So how do you ask the best questions that will then allow you to feed back in and do the quickest job of remediating? And those may not be the questions that we had in our data here.
So you'll learn, given the policy, you'll learn?
We're learning given conversational logs. We don't even have a procedural representation of the policy, but just the logs of it running. That's great, yeah. Any other questions? I apologize so quick on the conversations.
So, if you go back to just the previous slide, it'd be very surprisingly close to the supervised approach. So, do you know, I mean, this is on the same data set, but just with the full representation through supervision?
That's right.
So, do you know, have you looked at the learning curves, like how much supervised data do you need to reach your approach of your unsupervised approach? Or, how
right.
More conversational logs? Do you have 10 times as many logs?
That's a great question, yeah. And the only issue here, and this is something that we're looking into for the future, is that our data sizes aren't too big, right? So we looked a little bit at those curves, and they were a little bit noisy just because the data is so sparse. And so we were doing some bootstrapping and stuff, but then in the end we were kind of not convinced due to the size of the data, so we didn't want to present those curves. But in the ideal scenario, I think the way you would ideally want to do this learning is you would build a dialogue system, and in the dream scenario, you would deploy it. People would want to use it, and then it would sort of improve itself over time. And that's really the long-term goal here. And in those kinds of situations, the idea is you just never could possibly annotate everything. You'll hopefully, in the dream scenario, have more data than you can ever afford to touch. And in that scenario, you would just be forced down this route. You have other questions?
Yeah, some questions by Collins is that essentially have lost informed center. How much better does it do compared to regular perceptron?
Okay, those are both great questions. So the regular perceptron compared to the loss sensitive, the key idea is whether you have supervision, right? So the loss sensitive is looking at a loss function as supervision as opposed to labels, at least in the way that we used it. So it's a different setup. Right. So that's the trick. Is actually I cited it, but we actually made it an extra twist. So you can think of us as doing the hidden variable version of what they were doing. So we actually changed it even more beyond that, but we were using the same basic intuition of the updates. And so basically the same thing comes up for Myra too, right? I'm sure there is a version of thinking about the margin in terms of the sets that we had. And if you did that version of margin and not just separating by an amount, but actually being a little bit more hinge-loss motivated, you could recreate the same thing with Myra here. So you'd be maybe a little bit more aggressively doing bigger updates instead of just bumping in the right direction. I'm sure you could. I don't know how well it would work. Probably would work better, but it would be more computation.
That's just a really simple question. How long did it take you to train anyone?
That's a great question. Yeah, wall clock time, exactly. That's a great question. So the dialogue stuff is pretty quick. The loss isn't that hard to compute. You can pre-compute those sort of structures that I talked about that you were going to do the alignment onto. So you only really have to do that once per example. So that runs fast. I can't remember on the order of hours. The original grammar induction stuff ran pretty fast. Once you factor the lexicon, the parsing problem goes a bit crazy. So it turns out those experiments took a long time to run, and that's a current area of research. I think it was even 30 or 40 hours or something to run those experiments, which is embarrassing given that it's a semantic parsing problem. So we're working now on sort of improved CCG parsing algorithms. And the real issue there is the lexicon is just huge, right? And you have this as the grammar constant, and it just really kind of gets out of control if you're not careful. Okay.
Well, I've asked that for somebody else.
Okay, well, if you in the future you switch to full data coverage supervision, do you think you need, and if you need supervision, how do you get a people annotate that move?
That's right. So the goal, I don't have a good answer for how much supervision you'll need. The goal is to sort of annotate however much it wouldn't hurt for me and a grad student or two to do, which is, we could probably do tens or hundreds of dialogues. I'd be willing to do that. I have a certain tolerance for pain of annotation. But the goal would be to have just, tons and tons of unannotated stuff and to actually be able to improve from it. And the way you would get that is by building systems that people want to interact with. And so I don't know how to do that. That's a hard thing. But that's kind of the dream, right? Okay.
Do you really need to know what the speech echo is? Like, can't you just actually look at a phone conversation between a human and a user?
Right.
Maybe the user mumbled something and asked a clarifying question.
That's a great question. So I'll rephrase it slightly differently, not just about speech acts, but in general, what are the differences between human-human and human-system interactions, right? the key thing is that the style of interaction is just fundamentally different. I mean, human-human conversations are much more fluid, much more interesting, and they're much, much more challenging for learning perspective, right? Whereas human-system interactions are constrained. It's almost like having the database schema to talk about, right? Because the system is going to gather certain facts and execute certain queries and so forth. So you're sort of in this domain where you're constrained to talking about flights or something, and you even have this notion of the well-defined semantics to start with. So, you know, in terms of speech acts or not, we probably could imagine thinking of automatically inferring the speech acts or somehow getting them a different way, although they did come free from logging the system. So you probably could do something there, but it's a much bigger issue of moving to human-human than just the speech acts, and it's very challenging in general to learn from that.
How about just learning from answers to the questions?
This is like database tuples?
Yeah.
That's a fascinating problem. I don't have any contributions on that yet, but that's a really interesting thing that Percy's done lately. And the UIUC folks, Dan Goldwasser, who did it first. Other questions?